From today, we are going to start complex analysis from Brown and Churchill's book. And let's start from the very beginning with complex numbers. In this first section, we are going to see the operations of addition and multiplication of complex numbers. We define complex numbers like this. A complex number is by definition an ordered pair of real numbers. So if you look at this definition and think of it for a moment, complex numbers are actually nothing entirely new to us. We have already known complex numbers for a very long time. You recall that in school you were taught how to draw graphs of equations, graphs of functions, graphs of equations. What did you do there? You have the graph paper. First you drew a table of some values, some pairs of numbers. For a given input x, you calculated the output y if it's the graph of a function, and then using those numbers you plotted points, and you also labeled those points with their coordinates. The coordinates, two coordinates are taken together and written as an ordered pair. So those are ordered pairs of real numbers. But now suddenly, why are we calling them complex numbers? What is the reason for this new name? That's because at that time when you used them for locating points in the plane, points on the graph paper, there was no addition or multiplication involved of these objects, these ordered pairs of real numbers. Now, however, we are going to see an algebra of these objects. But before we see those operations, let's first understand one thing very clearly, that for two complex numbers z1 and z2, which are these ordered pairs, suppose x1, y1 and x2, y2, they are considered to be equal if and only if the corresponding coordinates are equal. That means x1 is equal to x2 and y1 is equal to y2. This is the definition of equality of two complex numbers, and this is also nothing new to us. We already know this from coordinate geometry. Now, given a complex number z, which is this ordered pair x, y, we call x the real part of z and y the imaginary part of z. And we have notations for this also. The real part of z is written like this, Re of z. Re stands for real, and the imaginary part is denoted by this notation, Im of z. Im stands for imaginary, respectively. That is, Re of z is x and Im of z is y. How justified are we to say that x is the real part of z and y is the imaginary part of z? Why do you think can a complex number not have two different real parts? That fact comes from this definition of equality. Once you have a complex number, its first coordinate is uniquely determined because of that definition of equality, and the second coordinate is also uniquely determined. That is why when you talk about real part of z, there is only one real part, and similarly there is only one imaginary part for a given complex number. Now, before we see anything else about these objects, you note this fact carefully. So basically, the set of all complex numbers is just our familiar R2, which is the Cartesian product of the set of real numbers with itself. However, we will denote this set by this letter C to indicate that we are talking about complex numbers. But when you use this, it means not just the set itself, but the operations of addition and multiplication of complex numbers, to which we now turn. Now we are going to define them. So let z1 equal to x1, y1 and z2 equal to x2, y2 be two complex numbers. Now using them, we are going to define addition and multiplication, that is their sum and product. Sum is defined like this, which looks quite straightforward. It is straightforward. So the sum is again an ordered pair of real numbers, where the first coordinate is the sum of the first coordinates of z1 and z2 and the second coordinate is the sum of the second coordinates. That's it. Note carefully. See, there are a few things that you have to note immediately when something new like this is defined, an operation. You may be familiar with this fact from algebra, but anywhere in mathematics when you define something new, you have to see whether it's well defined. That what you have defined, whether it even makes sense or not. So, we are given z1 and z2. And what did I say just now, that when two complex numbers are given, their real parts and imaginary parts are uniquely determined. For this z1, there is only this x1, which is its real part, and y1 is just its imaginary part, nothing else. So once you have chosen z1, these are unique, x1 and y1. Similarly, x2 and y2 are unique. Because x1 and x2 are unique real numbers, their sum is a unique real number. This sum is ordinary addition of real numbers. Similarly, this is also a unique real number. So this is a unique ordered pair of real numbers. That means it's a unique element again in C. So for two complex numbers z1 and z2, their sum is a unique complex number. That means this sum is a well-defined binary operation on this set C, which is actually nothing but this set. The product, however, looks a little complicated, but still let's see what it is. Here, the first coordinate is real part of z1 times real part of z2 minus imaginary part of z1 times imaginary part of z2. The second coordinate is, however, this real part times imaginary part plus real part of that other complex number times imaginary part of that other. Okay, so x1, x2 minus y1, y2, and this one is x1, y2 plus x2, y1. It looks quite complicated at first, but we will soon see that in spite of this complicacy, we still get those very familiar properties that we have for ordinary multiplication of real numbers for this multiplication also. But is it also a well-defined binary operation? That question is always there. So obviously again x1, y1, x2, y2 are unique. So because of that, this is again a unique real number and this is a unique real number. These real and imaginary parts of the product are not as easy as this, which are just sums. Here you have multiplication of real numbers, difference of real numbers, all those things are there. However, in spite of this complicated combination, for given x1, y1, x2 and y2, this is again a unique real number and so is this. So this is a unique ordered pair of real numbers, or in other words, a unique complex number. So yes, multiplication is also well defined. What does this all mean? It means that if you are given two complex numbers z1 and z2, first of all, the sum exists. Then the second thing is that it is unique, and the third thing is that it is also a complex number. The same is true for product also. Now next we are going to do something which at times looks very confusing, but you still keep seeing this here and there in mathematics. This. We identify the real number x with the complex number x, 0. What do we mean by this identification actually? It sounds confusing. Sometimes we are not really told anything more than this. Okay, it's a remark like this just appears and that's it. We don't quite understand what it means. This just means that we are considering the following function from the set of real numbers. Let me just give it any name, say f. from the set of real numbers into the set of complex numbers, and the function maps the real number x onto this complex number or this ordered pair x comma 0. Oh, and by the way, one more thing, you may notice this colons before the equals symbol. It indicates that we are defining something. Here, for example, we define this sum. It is something new, which by definition means this which we already know. Okay. The colon will lie on that side where the unknown symbol, something which is being defined, lies. Whereas on the other side, its meaning lies, which we already know. Same thing here, same thing here. But what does this function do? Why are we even considering this, and in what sense is this an identification? Why are we even using the word identify? So we have the two universes. One universe is the universe of real numbers. Universe sounds very dramatic, but actually just sets. The other universe is the universe of complex numbers. The objects that you have here are fundamentally different from the objects that you have here. Those are real numbers. These are ordered pairs of real numbers, different types of objects. So, really we cannot say that this is a subset of this. Strictly speaking, it is not. But we can say so, and we normally do so via this identification. It is, in what sense are we saying that we are identify these things? It is in the sense that we are thinking of this x comma 0 as that x. It is really not, but can we think like that? And if we do, using this function, what is the consequence? Say you do something in this universe, namely you take two real numbers x and y and take their sum, that is x plus y. Correspondingly, because you have this identification, you do the similar thing in this other universe. You can think of it as a mirror world. These are the real objects and these are their reflections. So if two actual objects do something, say they come close to each other, the reflections also come close to each other in the mirror world. So the corresponding thing that these two reflections do is that you consider their sum in the mirror world. This sum, however, is complex number addition. And using the definition that we saw for that sum, this is x plus x comma 0 plus 0, which is x plus y comma 0. So here you should have the ordered pair x plus y comma 0. Is the function not associating that with this x plus y? Yes. Alright, but then what are we achieving from this? We are achieving this, that no matter in which world you are looking, whatever happens here, an exact replica happens here. Whether you see the calculation happening in this world or this world, it does not matter. At least as far as addition is concerned. Is it also the same with multiplication? Let's see. So when you think of multiplying two real numbers, you just get their product. That also has a separate definition of its own, not going into that. But instead, if you multiply their reflections in the complex world, then what do you get? Let's apply the definition carefully first, because complex multiplication is really complex. The first coordinate will be real part times real part minus imaginary part times imaginary part. I did not write anything in between, but this is multiplication. Multiplication of real numbers, 0 and 0. And the second coordinate is real part times imaginary part plus imaginary part times real part. So yes, we are getting x, y as the first coordinate and 0 as the second coordinate, which is what this f associates with this in the real world. So you see that no matter what you do, whether it is addition or multiplication, if you are doing it in the real world, a corresponding replica is, a corresponding something is happening in the complex world which looks exactly like this one in the reflection world. What does this all mean? It means that you have found a part of C which behaves exactly like R. It's only a small part of C, but still it's a part of C which behaves exactly like R. In what sense? In the sense of applying these two operations. And if you look carefully, you will find very easily that this function f is also one-to-one. It's injective. If you have two different objects in the real world, then their reflections in the complex world are also different. They are not the same. And that is why we normally write like this, that R is a subset of C. It does not mean that R in its original form literally is a subset of C. It is not. But there is a copy of R inside C. That is, a part of C behaves exactly like R, and there is no point distinguishing these two. Okay, so that's how we have to interpret this. And now next we are going to see something which is familiar to us, because most of us already have seen complex numbers in the form x plus iy. We don't see that here. We seem to have defined complex numbers entirely differently as ordered pairs of real numbers. But then are we looking at something else? No, actually we are not looking at something else. And now we are going to get back that x plus iy. Let's see how. Say your complex number is z, which has real part x and imaginary part y. By the definition of addition of complex numbers, this equals this plus this. That's pretty easy to see. X plus 0 will be x and 0 plus y will be y. Okay. Now we keep this calculation hanging here and consider this product of the two complex numbers, the first of which is 0, 1 and the second one is y, 0. So what shall we get? The product of the real parts, which is 0 times y, minus the product of the imaginary parts, 1 times 0. I used a dot here, otherwise it would look like 10. And then the second coordinate is real part times imaginary part plus imaginary part times real part. So you see that this is just this 0, y. So that means z now becomes this x, 0 plus 0, 1 times y, 0. Now because of our identification, note that in place of this we can write x via that identification. Okay, this x actually really means f of x, where f is that identification function. Similarly, this y, 0 can be written as y. Don't write 1 here, okay, because it's not the type of ordered pair with which you are identifying real numbers. However, this complex number is very interesting, 0, 1. Let's calculate the square of this complex number. So, because we want to apply the definition of multiplication and it's still new to us, may not be new to many of you, but still in general say it's new to us. So I have written like this, 0, 1 times 0, 1. So by the definition of multiplication, complex multiplication, it will be this ordered pair where the first coordinate comes like this, real part times real part minus imaginary part times imaginary part, and the second coordinate is real times imaginary plus imaginary times real. So you are getting the complex number minus 1, 0, which however is the type of number that you can associate with the real number minus 1 via that identification. So it's an object whose square is minus 1. So does that remind you of something? So it is that familiar imaginary unit I. So we are giving this complex number the name I, because I is a name that I am defining. So again I am using that colon here. I means this, but then you use that here, and that's how you get your familiar expression. Z is equal to x plus iy, where x is the real part and y is the imaginary part. But sometimes means in elementary introduction to complex numbers, this is how complex numbers are introduced, and there is nothing wrong with that. This is also a legitimate way of introducing complex numbers, but with one caution, that when you introduce a symbol like this, where x is a real number and y is a real number, you have to carefully make this clear that this plus does not really have any meaning of its own, at least when the symbol is being formally defined. This is a formal symbol. If this is how complex numbers are introduced or defined. Formal means having the form of something, which you already know. It has the form of a sum, but it's not an actual sum, because this sum is not the sum of x and iy when complex numbers are introduced for the first time. Similarly, this product does not mean you are multiplying I and y. It just simply means that you have a composite object in which only x and y have meanings of their own. They are real numbers. Besides them, the other parts of this composite symbol, that is this plus and I, they do not have any meaning of their own. But from there itself, we have a lot of confusion. However, if you more rigorously introduce complex numbers as ordered pairs of real numbers, then you can recover this, and then you can do whatever normally you do with complex numbers. You can continue to do those things. Next, we have section 2, where there are basic algebraic properties of this system. Now you have a set and two operations on it. This system has some properties. Because most of us are already familiar with those properties, so I am going to be brief here. And all of this can be summarized in just one line, one or two lines. Namely, that this system consisting of the set of complex numbers, addition of complex numbers and multiplication of complex numbers is a field with R as a subfield. R means that R, the copy of R that C has inside of it, which behaves exactly like R, that is a subfield of this field. But let me just elaborate a little bit what this even means. Suppose you take any three complex numbers, Z1, Z2 and Z3. Then addition and multiplication are both commutative. The same things are true for real numbers as well. Just like that, addition and multiplication are associative. Again, real number addition and multiplication are also associative. Next, with this 0, 0, this complex number which we are calling 0, either you write ordinary 0 here via that identification, because it's the type of number that you can associate with a real number, this specific number being associated with the real number 0. Or you consider it as this itself for any complex number Z1, Z1 plus 0 is equal to Z1. This is what you also have when you consider real numbers. And just like that, if you consider the complex number 1, 0 and multiply it with any complex number Z1, you get Z1. Why am I not mentioning that fact also, which says that Z1 is also equal to 0 plus Z1? There is no need to mention that separately, because addition is commutative. Just like that, because multiplication is commutative, that just means, along with this thing, that 1 times Z1 is also equal to Z1. And that's why 0 is called an additive identity and 1 is called a multiplicative identity for the complex numbers. And here 0 means this and 1 means this. Next, number 4, fourth property. If the complex number z1 has real part x1 and imaginary part y1, then you think of this other complex number where the real part is minus x1 and imaginary part is minus y1, and we are giving it a name also, minus z1. By minus z1 we mean this. If so, then the sum of z1 and minus z1 using the definition of complex addition is that 0, that additive identity. And this minus z1 is called an additive inverse of the complex number z1. I am saying that these things are brief still because I am not proving these things. Okay, they are left to you. They are just routine things. You can verify them yourself. Then we have this distributive law. So far, whatever you have seen, those properties involve, each one of them involves only one operation at a time, either addition or multiplication. This one, however, combines them. z1 times z2 plus z3 equals z1 z2 plus z1 z3. And there is another one where this z1 is on that side. But that need not be mentioned because multiplication is commutative. So from this itself that automatically comes. And finally we have another one. Suppose z is a non-zero complex number. That means z has this real part, this imaginary part, and that's not equal to 0, 0. Then by the definition of equality of two complex numbers or equality of ordered pairs, both x and y are not simultaneously 0. One of them may be 0, or say both are non-zero, but both are not simultaneously 0 because otherwise this would be equal to this. But if both of them are not 0, then the sum of their squares is non-zero. It's a property of real numbers that you already know probably. But anyway, what does that do? It allows us to then consider this complex number, where you can see that we are dividing x and minus y by this real number, x square plus y square. And we can do that because it's non-zero. Okay, so this is a legitimate complex number. X divided by that, comma, minus y divided by that. And we have given it a name also, z to the power minus 1 or z inverse. So you can understand that this complex number can be considered only when z is non-zero. And it turns out that if you multiply z and this using the definition of complex multiplication, you get 1, and this 1 is 1, 0. So this is called a multiplicative inverse of z. That means every non-zero complex number has a multiplicative inverse. Just like every non-zero real number has a multiplicative inverse which is its reciprocal. Here it's not reciprocal, or if you want you can call it reciprocal, but it's this which is much more complicated. But still the same thing is true here. So whatever algebraic properties the system of real numbers has, the exact similar algebraic properties the system of complex numbers also has. Saying all these things and saying that the system of complex numbers is a field, they mean the same thing. So what do we achieve by constructing the system of complex numbers? Because it is so complicated, the name itself is complex numbers. Although that has nothing to do with complexity, when we already have the system of real numbers and it seems that this new system has exactly same properties that the old system has, are we even gaining anything? Yeah, of course we gain something very important, namely that equations can be freely solved within the system of complex numbers. You are familiar with equations formed within the system of real numbers which have no real solutions. For example, x square plus 1 equal to 0 has no real x for which the equation is satisfied. But the complex number I, that's 0, 1 satisfies it. There is another one, minus I. So after these exercises come, most of them are, all of them are left to you except this last one. Let's just see what it is. And this is about solving an equation, a polynomial equation, but within the system of complex numbers. The equation is this: z square plus z plus 1 equal to 0, which we have to solve for z, which is a complex number. So in the solution, we consider the polynomials separately. So if you write x comma y in place of this is what you will get. Now you carry out the multiplication and you will get this. You can see it yourself, okay. X squared minus y squared comma 2xy. And if you add these two things up, you are going to get x plus 1 comma y plus 0, that is y. So ultimately, this is what you are getting. Now if this complex number has to be equal to 0, 0 here means 0 comma 0. Then by the definition of equality of two complex numbers, both real and imaginary parts have to be 0. Okay, so this is 0 if and only if this is 0 and this is 0. In these two equations, however, we do not have complex numbers anymore. We have only real numbers. X and y are real numbers. Now if it happens that y is 0, it's a possibility. Let's see if it actually is a possibility. Then from the first equation we get x squared plus x plus 1 equal to 0. But this quadratic equation where x is supposed to be real has no real solution. You find the discriminant, you will find it's negative. So there is no real solution. So that means y actually cannot be 0. And because y is non-zero, you can divide both sides of this second equation by y, obtaining 2x plus 1 equal to 0, from which you can solve for x and find that x is minus 1 divided by 2. So you have found x. And then you use this x value here in the first equation and solve for y. Doing that, you will get two values of y. I leave the actual calculation to you. You will find that y is square root of 3 divided by 2, either that or negative of that. So that means you are getting two complex numbers as solutions of this complex equation, both of which have this real part and the imaginary parts are this or its negative.